it's really great pleasure to have Professor Edwin Witten. So he will tell us about an algebra of observables for digital space. Please start.
Well, thanks so much, Tadashi, for the introduction and also the invitation. So there are a couple of recent papers indicated here that I'll talk about, but I want to mention that the inspiration came from two previous papers by Liu and Luthhäuser that are indicated there. So I'm going to begin just with 5 or 7 minutes reviewing a couple basic facts about black hole thermodynamics to orient us to the language I'll use later. So apparently it was first Raphael Sorkin who suggested that Bekenstein-Hawking entropy of a black hole is some kind of entanglement entropy. And Sorkin's idea was the following. In quantum field theory, divide space into two regions, A and B. In Sorkin's application, B is the region behind the horizon of the black hole, A is the region outside, but I'll make some general comments that would apply to any two regions. Then Sorkin considered a state psi of the whole system. And given such a state, you can try to define its reduced density matrix for measurements only in one region, say region A, in the case of the black hole, the region outside the horizon. And then you can try to calculate the von Neumann entropy of this density matrix. And Sorkin's idea was that roughly the Bekenstein-Hawking entropy would be the entropy of such a state for an observer who's only making measurements in region A, so that what that observer sees is only the density matrix rho A. And therefore, this would be the appropriate entropy for that observer. Sorkin, however, found that this entropy is ultraviolet divergent, and the leading divergence did not depend on the state. The divergence was an ultraviolet divergence. In quantum field theory, all states are the same at short distances. So regardless of the state, you get the same leading divergence. And the coefficient of the leading divergence was proportional to the area A of the boundary between the two regions A and B. Well, Sorkin did get an entropy proportional to the area, but of course he had an infinite coefficient, whereas Bekenstein and Hawking had a coefficient 1/4g. But Sorkin had ignored gravity, which is like taking g to 0, so you could hope that Sorkin's divergent answer is the correct answer if you ignore gravity. And Sorkin was hoping that gravity would cut off the divergence and give a finite answer. Now, the next major advance I'll mention was by Susskind and Uglum a decade later. They made a simple observation. So I should say, Bekenstein had proposed a formula for the generalized entropy. He had proposed that a black hole itself has entropy A/4g, h bar, but ordinary matter outside the black hole have ordinary entropy, which I'll call S out. And Bekenstein's idea was that the generalized second law doesn't apply to ordinary entropy only, because I could take a cup of tea and throw it into the black hole, and then the ordinary entropy goes down. However, the area of the black hole horizon then goes up. And Bekenstein proposed that the second law really applies to this generalized entropy, the area over 4g h bar, which is black hole entropy, plus the ordinary entropy outside. While Susskind and Uglum were the first to observe that the generalized entropy is better defined than either term is separately. The second term has an ultraviolet divergence, which I already mentioned and which Sorkin noted. But the first has a similar problem because there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. When Hawking did his famous work justifying Bekenstein's proposal about black hole entropy, he did not take into account loops that normalize Newton's constant. The Newton's constant in Hawking's paper was a bare Newton's constant. But when we use this formula in the real world, we presumably have in mind the physical observed Newton's constant. The relation between the two is ultraviolet divergent, and at one loop, it has the quadratic divergence I've indicated. Now, Susskind and Uglum argue that the ultraviolet divergences in S out cancel those in the area term that come from divergences in 1/g. And these arguments were refined later. So it came to be understood that the generalized entropy is better defined than either of the two terms on the right-hand side of the formula. We can take that to mean that the entropy of a region is better defined in gravity than it is in ordinary quantum field theory. In gravity, if you try to compute the entropy of a region, you get Sorkin's ultraviolet divergence. If instead you use the Bekenstein formula, the divergences cancel, as shown originally by Susskind and Uglum. So gravity somehow makes the entropy of a region better defined than it would be without gravity. And that's something we'll discuss further later. Now, at this level, we could be talking about either a black hole horizon or a cosmological horizon. And in this talk, I'll discuss both, but I'll concentrate a little bit more on de Sitter space with the cosmological horizon. So in this talk, I'm going to aim to give a slightly abstract explanation of why entropy is better defined when gravity is included, at least for the basic examples of the black hole and de Sitter space, although I hope the lesson is more general. First of all, let's discuss the origin of the divergence in Sorkin's calculation. In ordinary quantum mechanics, when we consider entanglement between two systems A and B, we usually assume at the start that each system has its own Hilbert space, HA or HB. Then the Hilbert space of the combined system is a tensor product. Now, a state psi AB in the combined Hilbert space could be a simple tensor product of states of the two systems separately. In that case, systems A and B can separately be described by pure states, namely psi A and psi B. And there's no entanglement or entanglement entropy. But a more general state is not a simple tensor product, but a sum of tensor products like this one. In that case, we say that systems A and B are entangled, and each system separately has a non-zero entropy. Now, the point of this elementary slide has been to remind us that in ordinary quantum mechanics, whether or not a state has non-zero entanglement and entanglement entropy is a property of the state, not the system. That's not so for entanglement entropy between different regions in quantum field theory. In Sorkin's setup, the divergence is an ultraviolet divergence, so as I already said, it does not depend on the state. Every state looks like the vacuum at short distances, and therefore has the same leading divergence in the entanglement entropy. There aren't any unentangled states. The root of the problem is that in quantum field theory, it's not true that there are separate Hilbert spaces, HA and HB, for the inside and outside regions. There's only a combined Hilbert space H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables that I'll call curly A and curly B. These act on the physical Hilbert space of the system, so they can be defined as von Neumann algebras. A von Neumann algebra is just a fancy name for an algebra of bounded operators on a Hilbert space that's in which certain kinds of limits are allowed. Now, broadly, there are three types of von Neumann algebra. The one which we take for granted without even mentioning it is a type 1 algebra, the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss the system A, it has a Hilbert space HA, and the algebra of observables of the system is, roughly speaking, the algebra of all operators on HA. For some purposes, you might want to say that they're bounded self-adjoint operators, or maybe just self-adjoints. But roughly speaking, all operators are allowed. In ordinary quantum mechanics, we consider all operators to, in some sense, be physically sensible. And that's by definition a type 1 algebra, all operators on a Hilbert space. Now, in the type 1 situation, you can have densities and entropies. And, well, I had an elementary slide where I explained a little bit of that, but I'm going to assume that we're basically familiar with densities and entropies in ordinary quantum mechanics. The other types of von Neumann algebra are less familiar, and I'll give examples later, but first the bottom line. A type 2 algebra is an algebra that does not have pure states, but there is a notion of density matrix and entropy for a system in which the algebra of observables is of type 2. A type 3 algebra is the worst type. A system whose observables form a type 3 algebra does not have pure states and also does not have density matrices or entropies. Now, by now, from what I've said about Sorkin's ultraviolet divergence, you might anticipate the bad news. In quantum field theory, the algebra of observables of a region of space-time, as in Sorkin's picture, is always of type 3. So this is a result that goes back to Araki. Sorry. Approximately 1965. That might not be the exact year. So to a region, we can never associate a pure state or a density matrix or entropy. The algebra is of type 3, so the notion of density matrix and entropy isn't really applicable in quantum field theory. And we can view this as the reason for the universal ultraviolet divergence of the entanglement entropy. When we try to define entanglement entropy in quantum field theory, we're using a concept that doesn't strictly apply. It would apply in a lattice cutoff theory, for example. In a lattice cutoff theory, you would have an inside and outside Hilbert space. There can be some subtleties in a lattice gauge theory, but for simplicity, in a lattice scalar field theory, the big Hilbert space would be a tensor product of inside and outside Hilbert spaces. And the outside observer could have a type 1 algebra, all operators on that space. And then you'd have a type 1 algebra. The only problem being that the states that are unentangled are very far from the continuum limit. In the continuum theory, you have a type 3 algebra, and that's the reason that you have trouble when you try to define density matrix or entropy. Well, I put the reason in quotes. That's an abstract explanation of the reason. However, and this is the main point of my talk, including gravity in a semi-classical way changes the picture. At least in the case of the black hole or de Sitter space, including gravity semi-classically changes the algebra from type 3 to type 2. So turning on gravity, even in the limit that Newton's constant is arbitrarily small, will give us a type 2 algebra where density matrices and entropies are meaningful notions. So when gravity is turned on, even for recoupling, the region outside the horizon is described by an algebra in which there is a notion of entropy, though there is no notion of a quantum mechanical microstate. Type 2 and type 3 algebras do not have microstates, but they do have density matrices and entropies. We get a type 2-1 algebra for de Sitter space and a type 2 infinity algebra for the black hole. Well, what are type 2 and type 3 algebras? Roughly, type 2 and type 3 algebras are the natural operator algebras that act on a system A that has an infinite amount of entanglement with another system B. So whenever you have an infinite amount of entanglement, the algebra of observables are of type 3. For today's lecture, we're interested in quantum field theory in a region, but another problem that has an infinite amount of entanglement is quantum statistical mechanics in the infinite volume limit. There's an infinite amount of entanglement, and the algebra is of type 3, in fact, in quantum statistical mechanics in the infinite volume limit. Anyway, in quantum field theory for operators in a given region of space-time, we always have an infinite amount of entanglement between modes just on one side of the border between the regions and modes on just on the other side. So modes close to the separation between the two regions are highly entangled with always an infinite amount of entanglement. And likewise, as I already said, in quantum statistical mechanics for an infinite system at positive temperature, there's always an infinite amount of entanglement. So such systems are not going to give type 1 algebras because they have an infinite amount of entanglement. In fact, without gravity, they lead to type 3 algebras. A type 2 algebra is more special than a type 3 algebra, but since our goal will eventually involve type 2 algebras, and also because the explanation is a bit shorter, I'll start with type 2. For us, there actually are two important types of type 2 algebras, type 2-1 and type 2 infinity. A type 2-1 algebra is most simply the algebra that acts on an infinite collection of qubits that are in an almost maximally mixed state. So we could consider n qubits that are in an exactly maximally mixed state. Here I've considered the system A, which has n qubits, the system B has n qubits. The nth qubit of system A is completely entangled with the nth qubit of system B. So system A is completely entangled with system B. Now let A and A prime be operators that act on only the first k spins or qubits of system A, where k is no bigger than n. We're eventually going to take n to infinity, keeping k fixed. Then we define a function f of A, which is the excitation value of A in the state psi. Well, I chose A to be maximally mixed, so its density matrix is 2 to the minus n times the identity. So f of A is the trace of A times the density matrix, and that's 2 to the minus n times the trace of A. The trace is the trace in the Hilbert space of system A, because A is an operator on system A. Now, from this formula, you see immediately that f of A prime equals f of A prime A, because they're both multiples of the trace of A prime. Another fact is that f of 1 is 1, because the state was normalized and the density matrix had trace 1. And finally, and this is the key fact, f of A has a thermodynamic limit, meaning it's unchanged if we add more maximally entangled spins to the system with the given operator little a, with the given operator A, not acting on the added spins. So we consider the limit n to infinity, and we consider any operator that acts on only finitely many qubits of system A. This function f of A has a limit as n goes to infinity because it's unaffected by adding more spectator qubits. And in the limit, it still satisfies f of 1 equals 1 and f of A prime equals f of A prime A, because it satisfied those conditions for every n. Now, so far we've defined f on the whole algebra, which are A naught, of all operators that act on only finitely many qubits in system A. But we can take the closure of A naught in von Neumann sense. That means we allow operators that act on any number k of qubits, but the matrix elements decay rapidly for large k. So we allow operators that can be approximated very well by operators that act on a finite set of qubits, but they don't strictly have 0 matrix elements to act on a larger number. So by taking this closure of A naught, we can complete A naught to a von Neumann algebra A, still with a function f of A that has the same properties I've stated. The reason we want to take this closure is that von Neumann algebras have a simple classification, but before we take the closure, the algebra depends on the details of the system. So to make simple statements, we take the closure, and then we have a very general and crude classification of von Neumann algebras. Now, since f of A prime equals f of A prime A, this function is usually called a trace, and I'll write it as one. So I'll write that f of A is the trace of A. But the trace of A is not the trace of A in any Hilbert space representation. It's more like a renormalized trace in which we removed an infinite factor 2 to the n, where n was going to infinity. We normalize it so that the trace of 1 is 1. Now, we did a certain amount of work to describe an infinite dimensional algebra with a trace, but there's a more elementary example you all know. The type 1 algebra B of all operators on an infinite dimensional Hilbert space H. In this example, we have a trace, which is just the trace in the Hilbert space. We take A to its trace in the Hilbert space. That's a trace, but it's not defined for all elements of B, only those that are trace class. For example, the identity element of B doesn't have a trace unless you want to allow infinity as a value. By contrast, from the infinite system of qubits, we constructed an algebra A in which every element has a trace. So clearly, it's an essentially new type of algebra. In fact, it's the simplest type of example of a type 2 algebra. It's said to be of type 2.1, and it's actually called the type 2.1 factor of Murray and von Neumann. Murray and von Neumann, I think in the late 30s, constructed it in essentially the way I've told you. Factor means that the center of the algebra consists only of C numbers. There are no operators other than C numbers in the center of this algebra. Factor is von Neumann algebra terminology that's analogous to simple for a Lie group. Now,
excuse me, can I ask a question?
Yes, please.
So you take this k to be finite to define
I
this type.
started with finite k.
So if we take k, if we allow k also can be infinite, so do you get a different algebra, or
Well,
it's not well defined?
it's in general not well defined. You have to say what you're doing when you take k to infinity. I said it roughly here. I didn't explain it completely. Here we took k to infinity, but in a restricted way. Well, okay. If we allowed completely general operators, yeah, we'd end up with something extremely wild that doesn't derive much wilder than you get in quantum field theory. Well, let's discuss the construction that leads to something nice. I think I'd rather use the time that way. Von Neumann said, yes, we want to take k to infinity, but we only want to allow operators that have very small matrix elements if k is very large. So we allow an operator that has matrix elements of order 1, let's say if they act on k qubits, but they're of order epsilon if you act on 2k qubits, and epsilon squared if you act on 3k qubits, and so on. So von Neumann, when we take the closure to get the von Neumann algebra, we allow operators that have non-zero matrix elements to act on any number of qubits, but the matrix elements to act on very many qubits are very small.
Huh.
To motivate it, you might think that our qubits are arranged on an infinite lattice. And then we want to consider operators that are approximately local. An approximately local operator mostly acts only on a finite set of qubits, the ones in the region it's acting on, but maybe we'll allow some weak long-range action. Or in quantum field theory, the infinite qubits correspond to modes higher and higher in the ultraviolet. And the operators we consider don't excite very high energy modes very much. So they mostly act on the low energy modes. But for different operators, they will act on different modes. If we take an operator higher momentum, it'll act on more modes. The cutoff in energies above which its matrix elements are small depends on the operator. But we only consider operators that are unlikely to excite arbitrarily high energies. Roughly, that's what this means.
Thank you very much.
If you try to consider all operators, it's too wild. If you want to read more, I did write an article which is called Why Does Quantum Field Theory in Curved Spacetime Make Sense and What Happens to the Algebra of Observables, where I explain more than I'll be able to explain today.
Thank you very much.
Now, as I was saying here, we all know a more elementary example of an algebra with a trace, infinite algebra with a trace. That's the type 1 algebra of all operators on an infinite dimensional Hilbert space. But in that case, not all operators have a trace. For example, the identity has trace infinity. And since the trace is infinity, we can't normalize it to make the trace of the identity finite. Then operators of finite traces would have trace 0. By contrast, from the infinite system of qubits, we constructed an algebra in which every element has a trace. So curly A was an essentially new type of algebra. And as I said, it's the simplest example of a type 2 algebra, originally introduced by Murray and von Neumann. Now, if A is this type 2-1 algebra and B is the more obvious type 1 algebra of all operators on an infinite dimensional space, we can make a third type of algebra as their tensor product. So C I'll write as A tensor B. The new algebra still has a trace because each factor does, but the trace is not defined for all elements because of the factor of B. In fact, C is a new kind of algebra said to be of type 2 infinity. And these are the important type 2 algebras, or at least for the type of applications in today's lecture. And there's only one type 3 algebra that's important for the, in quantum field theory, there's a universal type 3 algebra for any region in any quantum field theory, or at least that's believed to be the case. It's not completely proved, I don't think. It turns out that C is related to the black hole and A is related to de Sitter space. Now, what's an algebra of type 3? Well, to make an algebra of type 3, we do almost the same thing, but we start with the case that the kth qubit of system A is entangled with the kth qubit of system B fully, in the sense that the eigenvalues of the density matrix are not 0, but not maximally, in the sense that those eigenvalues are not equal. So I've written a simple example of a state where the kth qubit of system A is entangled with the kth system of qubit B with a thermal but not maximally mixed density matrix. We can still define the function f of A, and as before, it has a thermodynamic limit. And we can use that to define an infinite algebra following the same steps as before. The important difference is that now f of A prime is not equal to f of A prime because the density matrix is not equal to a scalar, not equal to a multiple of the identity. So, but nevertheless, we follow the same steps as before. For n to infinity, we construct an algebra A naught consisting of operators that act on any finite set of qubits of the A system. And then we complete it to a von Neumann algebra, which now is of type 3. And in fact, in the infinite volume limit of positive temperature, the algebra of observables of almost, well, of any quantum system is of type 3. Sorry. And what I've said is essentially, well, I think Murray and von Neumann had another construction, but the construction I've just told you of a type 3 algebra dates to the 60s also and is due to Powers, Araki, and Wood. Now, algebras of type 2 or 3 do not have an irreducible representation in Hilbert space. Another way to say it is that they don't have microstates. What a microstate would be a vector, a pure state, in an irreducible representation of the algebra. But these algebras don't have an irreducible representation. Whenever a type 2 or type 3 algebra acts on a Hilbert space, it always commutes with another type 2 or type 3 algebra. For example, in the construction I gave you of type 2 and type 3 algebras, as algebras that act on the A part of a bipartite system AB, in that construction, they commute with an identical algebra on system B. So in that construction, our type 2 or type 3 algebra commuted with another type 2 or type 3 algebra, and that's actually inevitable. The difference between a type 2 and type 3 algebra is that a type 2 algebra has a trace, and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that if f of A is any linear function on the algebra, then f of A is the trace of A prime for some unique A prime in the algebra. In particular, if A acts on a Hilbert space H and psi is a state in H, we can consider the linear function that takes A to its expectation value in the state psi. And because of what I just said here, that will be the trace of rho times A for some element of the algebra. So there will be some rho in the algebra that satisfies this condition. And since that's the condition by which density matrices are defined in ordinary quantum mechanics, it makes sense to call rho the density matrix. So a state of a type 2 algebra has a density matrix. Once we have density matrices, we also have entropies. We define entropies in the usual way, as minus the trace of rho log rho. So a state of a type 2 algebra has an entropy. However, I should warn you that in physical terms, the entropy of a state of a type 2 algebra is a sort of renormalized entropy from which an infinite constant was subtracted. So we constructed our type 2 algebra in the example I gave from a system with an infinite amount of entanglement. So in that construction, there was a maximally entangled state that we actually started with in making the definitions. So physically, it has an infinite entropy, but when we define the entropy of the type 2 algebra, we subtract that infinity and we measure all entropies relative to that one. So for example, if we go back to that system, let's go back to the case of finite n. In the maximally entangled state, the A system had entropy n, which is infinite in the large n limit. As an example of a state of the system, we could disentangle k qubits where we keep k fixed as n going to infinity. And that's similar to the fact that we started with operators that only act on k qubits. So an operator that acts on k qubits could project them onto a pure state and disentangle k qubits from the B system. So with the algebra we considered, we have to consider such states. Such a state has entropy n minus k. Entropy of a type 2-1 algebra could be defined by subtracting, I see, here I gave an abstract definition where it's not clear that renormalization was involved. But to give another explanation where it's obvious that renormalization is involved, entropy of a type 2-1 algebra can be defined by subtracting n before taking n to infinity. So then the maximally entangled state has entropy 0, and the state with k qubits disentangled has entropy minus k. And it's intuitively obvious that with this definition, if we subtract the entropy of the maximally entangled state, all other states will have negative entropy. That's intuitively obvious and not hard to prove. More formally, we define the trace by the excitation value in the maximally mixed state. So, in other words, but the density matrix of the maximally mixed state would be defined by this. So comparing the definition of the trace to the definition of the density matrix, we see that the maximally mixed state of a type 2 algebra has density matrix 1. That's indeed a density matrix because we define the trace so that the trace of the identity is 1. So 1 is a properly normalized density matrix. But the log of 1 is 0, so the entropy of the maximally mixed state is 0. And it's not hard to prove that any other density matrix has strictly negative entropy. Now, as I've already explained, in ordinary quantum field theory, the algebras of regions are of type 3. But it turns out, at least for the black hole and de Sitter space, that when we include gravity, things are different. Gravitational effects, even for very weak coupling, convert the type 3 algebras into type 2 algebras. That can be viewed as an abstract explanation of why entropy is better defined in the presence of gravity. For type 2 algebra, there is a well-defined notion of entropy. For type 3, there isn't. So the fact that gravity converts type 3 to type 2 can be viewed as an abstract explanation of why gravity makes entropy better defined. The details are somewhat different in the two cases of the black hole and de Sitter space, and I'll begin with de Sitter space. So here I've drawn the Penrose diagram of de Sitter space. So in this diagram, time runs vertically, and space, or really one direction in space, runs horizontally. A spatial section of de Sitter space is a sphere, let's say with a south pole and a north pole. The south pole and north pole are at the ends of the diagram, and you could think of the horizontal line as representing the latitude. And following Penrose, one's made a conformal mapping to map the picture to a finite picture, but the time is infinite at the top. It's minus infinity at the bottom. And the conformal mapping has been made so that light rays travel at a pi/4 angle to the vertical. The picture wasn't drawn very carefully, but the diagonal red lines are meant to be at a pi/4 angle to the vertical, so they represent light rays. Now we consider an observer who sits at the south pole of the sphere. In the diagram, the world line of the observer is simply the left boundary of the picture. And now we see that the observer has a future horizon, this diagonal red line up here, and a past horizon down here. And there's what's called a causal patch. The causal patch is the region that the observer can influence and also can see. It's the green region. The observer can then send a signal to influence something in the causal patch. You can also see what happens. So if you want to know what's out here, you can shine a light beam or a flashlight beam out there and see what comes back. So the causal patch is the region that you can explore actively. The region behind the past horizon, you can explore it passively. You can see what comes from there, but you can't disturb it. Now, de Sitter space has a killing vector field of time translations that's future-directed time-like in the static patch. The orbits look something like this. its path-directed time like in the opposite static patch, which would be the static patch for an observer at the North Pole. The opposite static patch is the region space-like separated from the static patch. That's this region over here. So let H be the generator of time translations. In ordinary quantum field theory in de Sitter space, there's a natural de Sitter state, sometimes called the Bunch-Davies state, but actually there are a bunch of early references on this state. It can be obtained by analytic continuation from Euclidean signature. And an observation that goes way back to the 70s is that correlations in this state have a thermal interpretation of the de Sitter temperature. The de Sitter temperature is 1 over beta, where r is the radius of de Sitter space and beta is the circumference, 2 pi times the radius. 1 over the circumference of the Euclidean sphere is the de Sitter temperature. And correlation functions in this state have a thermal interpretation at that temperature. A slightly abstract way to describe this thermal interpretation is to say that the modular Hamiltonian of the state psi ds for observations in this is for observations in the static patch is a multiple of the Hamiltonian. It's in fact beta times the Hamiltonian. Now, in ordinary quantum field theory, we dissociate to the static patch an algebra of observables, and as for any region in quantum field theory, it will be of type 3. Including weakly coupled gravitational fluctuations does not qualitatively change the picture. We could include gravitational perturbations as additional modes that we include in the definition of the Hilbert space, and we then include them in the definition of the de Sitter state, the Bunch-Davies state, and the algebra. What does change the picture is that in a closed universe such as de Sitter space, the isometries have to be treated as constraints. That means, now for us, the important isometry, first of all, since we'll be studying the static patch, what count are the isometries of the static patch? But the important isometry of the static patch is the time translation symmetry. So that's the one I'm going to focus on, although other isometries can also be considered. Just considering time translations, imposing the constraints means that we should replace the algebra of observables by A naught H, its invariant subalgebra, the subalgebra of observables invariant under time translations. But that doesn't work. The invariant subalgebra is trivial. Basically, any operator that commutes with H can the average over all the thermal fluctuations and replaced by its thermal average, a C number. So the only operators that commute with H are C numbers. Sorry. Any operator in the static patch that commutes with H is actually a C number. So A naught is a static patch algebra. So specifically for operators in A naught that commute with H, they're all C numbers. Now, therefore, if we leave the problem as it is, we're not going to get anything sensible. To get a reasonable algebra of observables, we have to ask who's making these observations. So we're going to include an observer in the analysis. Of course, in principle, an observer should really be described by the theory, not injected from outside. A theory of quantum gravity is supposed to give a complete description of the world, so the observer is part of what the theory describes. One way to explain what it means to include an observer is that we consider a code subspace of states in which an observer is present in the static patch. And then we'll consider operators that can be defined in the low energy effective field theory in this code subspace, though they're not well defined in the whole Hilbert space. Should we be surprised that we need to include an observer to get a sensible answer? I think you can argue that the answer is no. In ordinary quantum mechanics without gravity, you can consider the observer who studies the quantum system to be external to the system. With gravity included, the observer inevitably gravitates, and cannot truly be considered external to the system. Once you include gravity, either classically or quantum mechanically, anything in the world is part of the system. However, in an open universe, that means with non-compact spatial sections, for example, in an asymptotically flat universe, the gravity of the observer can be negligible. It's in a closed universe that it may be impossible to ignore the gravity of the observer. That's exactly the situation we're in here, because de Sitter space is a simple model of a closed universe, that is a universe with compact spatial sections. The fact that de Sitter space is a closed universe is what goes into the fact that we had a problem, that there aren't any operators in the static patch that commute with the constraints. And I think the physical interpretation is that if you want to discuss observers in the static patch, you have to take seriously the observer who's making the observations and include the gravity of that observer. So we'll now include the gravity of the observer and we will get a sensible answer. As a minimal model of the observer, we'll consider a clock with a Hamiltonian that I'll call Q. Or really, let me just say that I will endow the observer with a Hamiltonian. So if the observer is going to have gravity, the observer has to have energy. So we need, the minimum was that we need the observer to have a Hamiltonian so that we can talk about the gravity of the observer. It turns out that to solve our problem, we don't need a more elaborate model of the observer. An observer with the Hamiltonian is enough. So I give the observer a Hamiltonian Q. It's physically reasonable to assume the observer's energy is bounded below, possibly by 0 or maybe by mc squared, but I'll take the bound to be 0. So we assume that Q is non-negative. So the effect of including the observer is to modify the Hilbert space by replacing what it was before with what it was before tensored with square integrable functions on the positive half line. The positive half line because we took Q to be non-negative. Likewise, we extend the algebra. Before imposing the constraints, we had an algebra before of A0 that acts on effective field theory degrees of freedom, but now we have the observer's operators, and we'll assume that the observer can manipulate the observer's Hilbert space in an arbitrary fashion, which means we include the type 1 algebra, which I call B of L2 of R plus, which is just all operators on L2 of R plus. So if we don't worry about the constraints, then we extend the Hilbert space in this fashion, and we extend the algebra in this fashion. Now, finally, we have to take the observer's gravity into account in defining the constraints. The constraint was the generator of time translations. It becomes the total Hamiltonian of the quantum fields plus the observer. So the constraint operator is no longer what it was before. It's what it was before plus the Hamiltonian of the observer. The correct algebra of observables, taking into account the presence of the observer, is therefore modified in two ways. First, we extend the bare algebra, and then we impose a different constraint. Now, it turns out that when we do this, we get a very nice answer. The reason is that once an observer is present, we can gravitationally dress any operator to the observer's world line. We didn't have any operators before because there was no place they could be gravitationally dressed. In de Sitter space, because it's a closed universe, there's no region at infinity to which you can dress an operator, as you would do in asymptotically flat spacetime or asymptotically anti-de Sitter spacetimes. But if an observer is present, you can gravitationally dress any operator to the observer's world line. You do that simply as follows. For any operator in the quantum field theory, effective field theory algebra, you replace it by a dressed version, which is conjugated by e to the IPH, where P was the conjugate of Q. And that operator commutes with the constraint, which is now H plus Q. So a short calculation will show that this operator commutes with that one. So in contrast to before, where we had no operators that commute with the constraint, now we do have a lot of them because we can gravitationally address all the naive operators. One more operator that commutes with the constraint is Q itself, or equivalently minus H. Since H plus Q is the constraint, modulo the constraint Q is equivalent to minus H. So it doesn't matter whether we add Q or minus H to the algebra, but we get an algebra which is generated, a hat, I'll call it, generated by these operators little a hat and Q. Now, Kahn and Takasaki showed in the 1970s two facts. There are no more operators that commute with the constraints. And the algebra curly A that's generated by these operators, a hat and Q, is of type 2. Well, why did Kahn and Takasaki do this? They weren't studying de Sitter space. They were studying type 2 algebras. Well, sorry, they were studying type 3 algebras. Type 3 algebras were hard to understand because they were the hardest type of von Neumann algebra. They discovered this construction which can create a type 2 algebra out of a type 3 algebra. And importantly, they showed you can go backwards and essentially reconstruct the type 3 algebra from the type 2 algebra. So what they were doing was introducing a method to study type 3 algebras. For us, it's a natural physical construction in de Sitter space. It just happens that including the observer landed us on this classic construction of Kahn and Takasaki. Well, to be more precise, the algebra we get this way is of type 2 infinity if the observer energy is not bounded below. If the observer energy is bounded below, we get an algebra of type 2-1. Now, it's believed that de Sitter space in the presence of gravity has a state of maximum entropy. The state psi ds that can be defined by analytic continuation from Euclidean signature and represents empty de Sitter space. Often, as I said, called the Bunch-Davies state because of one of the original papers. So if we want to reproduce the fact that the entropy has a maximum, we have to assume that the observer energy is bounded below. But I think that's a very nice result because physically it's obviously a much more realistic model of an observer to assume that the observer energy is bounded below. And that gives us what we need for de Sitter space. Once we get a type 2-1 algebra, there's going to be a state of maximum entropy with density matrix 1. I'll explain that for the system with infinitely many qubits, but it's true generally for type 2-1 algebra. It's not difficult to identify that state. It's the natural de Sitter state of the bulk fields tensored with a simple vector in the Hilbert space of the observer, which roughly means that the state of maximum entropy is the de Sitter state that represents empty de Sitter space, tensored with the thermal state of the observer at the de Sitter temperature. So this is a satisfying answer for the maximum entropy state. So now we can draw a few easy conclusions which harmonize with claims made in the past by several authors. First of all, since the maximum entropy state has rho equals 1, you can compute its Rényi entropies and you find that they're independent of alpha, which was argued for de Sitter space by these authors. And these authors made claims that are related. Given the statement that de Sitter space has a state of maximum entropy, that's what you should expect. In ordinary quantum mechanics, the maximum entropy state of this system is maximally mixed with a flat entanglement spectrum. And its Rényi entropies are independent of alpha. Now suppose the observer makes a measurement with two outcomes that correspond to projection operators pi and 1 minus pi. The probabilities of the two outcomes are trace pi and trace 1 minus pi. All values of trace pi between 0 and 1 are possible, as shown by Marie and von Neumann. If the outcome corresponding to pi is observed, after this measurement, this is the density matrix. Since the two eigenvalues of sigma are 0 and 1 over trace pi, you can find that sigma log sigma is this. So the entropy after the observation is this one. The entropy reduction from knowing the outcome is this. And you find that the probability of the outcome is related to the entropy reduction by this nice formula. So that's a funny formula, though, because it shows you that the probability of making an observation is determined only by the entropy reduction if you make that observation. Whereas, since de Sitter space has a thermal interpretation, you would have thought that, for example, the probability to observe an elephant in de Sitter space would have a thermal suppression, the exponential of minus the elephant mass divided by the inverse temperature, times the inverse temperature. Now we see the thermal interpretation of de Sitter space predicts that the probability of low energy observation would be controlled thermally. So we have two different candidate formulas for the probability of seeing a given fluctuation in de Sitter space. One is thermal and the other is purely entropic. So, but for consistency of the two, we must have that the exponential of minus the entropy reduction is the exponential of minus beta times the energy. In other words, thermal suppression of a fluctuation can be understood as pure entropic suppression. That's surprising, but it's been argued before on other grounds, notably by considering the case that the fluctuation is a small black hole at the center of the static patch. Well, what part of this is surprising? The formula that the probability of an observation is the exponential of minus the entropy change is an inevitable consequence of a maximum entropy state in which all states are equally likely. In other words, if all states are equally likely, the probability of an outcome is proportional to the number of microstates, consistent with that outcome. That's language of ordinary quantum mechanics. A moment ago, we reached the same conclusion in the type 2.1 language. So the surprise is not that P is e to the minus delta S, but that the maximum entropy state also has a thermal interpretation. And I had hoped to talk about the black hole, but I see I'm running over with the time. So instead, I'm going to conclude by explaining how to see in the context of the type 2.1 algebra that the maximum entropy state has a thermal interpretation. So first, we ignore the constraint for a moment. We consider an operator A in the naive algebra, and its time dependence is defined this way. And then we look at time-dependent correlators, such as this 2-point function. And they have thermal properties that reflect the fact that they can be computed by analytic continuation from Euclidean signature. And that's the thermal nature of de Sitter space. After imposing the constraint, we replace A with the dressed version, A hat. And again, we define its time dependence by conjugating by the Hamiltonian. But then, because the Hamiltonian annihilates the de Sitter space, we trivially find that in the maximum entropy state, the 2-point function or any correlation function of the dressed operators is the same as was the correlators of the Baire operators in the Bunch-Davies state. So correlators of gravitationally dressed operators, after imposing the constraints, have the same thermal properties that correlators of Baire operators had before imposing the constraints. So in other words, we've reconciled the fact that de Sitter space is a maximally mixed state, which sounds like infinite temperature, with the fact that it also has a thermal interpretation at a finite temperature, the de Sitter temperature. And I will stop here. I had additional slides which would have, which involve explaining the story for gravity. So maybe we can put the slides on the website, but I think I'm out of time for the talk. So I'll stop here for questions.
Thank you very much. A beautiful talk. So it's time for questions. So if you have a question, please ask. And maybe could you raise your hand? Yes. Yes, please go ahead. Deepan.
Go ahead, Deepan.
Yes, sir. Sir, if we have a Big Bang singularity and a Big Crunch singularity, or any kind of naked singularity, will that affect the the suppression of the observables or any of the or any of the conclusions?
Well, the argument I gave is only for de Sitter space, unfortunately. And even if I had time to give this last part of the talk, it would have been only for the black hole. So I don't really know what happens for other spacetimes, but I will say that the most optimistic conjecture, maybe too optimistic, but the most optimistic conjecture of its type is that any observer who sees only part of the universe describes observations by a type 2 algebra. I don't know if that's true, but I view that as the most optimistic conjecture of its type.
And that will be irrespective of naked singularities within the static patch?
Well, perhaps you have in mind de Sitter Schwarzschild. So the
Yes.
de Sitter Schwarzschild spacetime has a past singularity.
Yes, sir.
So it would be good to study de Sitter Schwarzschild. It's a little trickier because the two horizons have different temperatures. So one can't trivially extend the things I've said to de Sitter Schwarzschild. I'm optimistic that an observer in de Sitter Schwarzschild would have a type 2 algebra, but I haven't analyzed that properly.
And would this statement hold true even for eternal limitation, where we have different forms?
Well, I've only called it a highly optimistic conjecture. If you want me to go out on a limb with a highly optimistic conjecture, then yes, I'm willing to make a highly optimistic conjecture that any observer who sees only part of the universe would describe all observations by a type 2 algebra. I don't know if that's true. That would mean that such an observer has density matrices and entropies, but no pure states.
Okay, thank you.
Giorgio?
Hi, thanks for a great talk. Is there a way to see this, I guess, the transition between type 3 to type 2 from a path integral point of view, maybe with Schwinger-Keldysh or something like that?
Good question. I don't know. I'd like to tell you something about the black hole, which is an intuitive way to see it for the black hole, but I don't have time to explain it. So the black hole, the two-sided black hole, is a globally hyperbolic spacetime with a Cauchy hypersurface S, and there's a conserved energy. There's a conserved charge associated with the killing vector field of time translations that goes forward on the right and backward on the left. And then heuristically, you might ask if the Hamiltonian, if the conserved charge is the difference of a Hamiltonian on the right and a Hamiltonian on the left. The answer to that is no. That's in the absence of gravity, that's false. You can't split the conserved energy as the difference in an operator on the right and an operator on the left. So this is no without gravity. So sorry, I'm not answering your question about path integrals. I mean, I changed the question to intuitive explanations. So I'm telling you the simplest intuitive explanation that I didn't have time for in the talk. I realize it's not exactly an answer to your question. Without gravity, you can't split the conserved charge associated to the killing vector field of the Schwarzschild spacetime as a right operator minus left operator. But with gravity, you can. H is the ADM Hamiltonian on the right minus the ADM Hamiltonian on the left. And the content of the part I just didn't have time for the black hole is really that the fact that you can make this splitting with gravity, but not without gravity, is the reason that with gravity, you get a type 2 algebra, and without gravity, you do not. So that's my best intuitive explanation in the case of the black hole, although it takes more time to explain why this fact is so important. But it wasn't based on path integrals, so it doesn't really answer your question.
That actually is relevant to Schwinger-Keldysh related.
Oh, okay. And I'm glad I may have said something useful, but okay. Anyway, I did the best. If the question had been what's a simple explanation in the case of the black hole, this would have been my best. Any more questions?
Yes, can I ask a question? So if we think, for example, digital space in global coordinate, so I mean, area across time slice is really exponentially developing, increasing, exponentially increasing. And in that case, cross-sectional area is exponentially also increasing and much larger than digital entropy. Do you think is it possible to understand this exponentially large area in terms of some algebra?
Good question. I don't know. I guess maybe people would speculate that it has to do with the entropy of the state or something. Oh, sorry, the complexity of the state or something. Analogy to what's been said for black holes. But I can't tell you anything from the point of view of the von Neumann algebras. I can't tell you anything at the moment.
I see. So do you think this type 2 algebra corresponds to some particular class of area in gravitational space-time? Maybe
I didn't have time for this. Sorry, this is a very important fact, which I didn't have time for. It's in the paper of one of the papers I mentioned at the beginning by Chandrasekhar. I'm abbreviating the names because of time. Longo, Pennington, and me. Oh, well, there are two papers. There's also just one by the three of us. We showed that the entropy defined in the type 2 algebra is equal to gravitational generalized entropy plus a constant, the constant independent of the state. So gravitational generalized entropy, I remind you, is A over 4G H bar plus S out. So you see, for my lecture to make sense, we need to know that the entropy I defined agrees with what people study by other methods. And I didn't explain that in this lecture. It would have been a different lecture. It is explained in two of the papers, one for de Sitter space and one for the black hole.
So but do you think this area is for any generic surface in?
No, it's the area of the horizon.
For horizon, I said.
Yeah.
But if we take some non-horizon, like minimal surface or more generic surface, do you think there are some chances that area can be interpreted as a type 2 algebra?
Well, if it's a minimal surface, you might think that it would be related to the operators to the left of the surface or to the right of the surface. I don't know. I'm not sure if I should state such a conjecture. I would need to think more. All I can tell you, when I said that entropy defined this way agrees with standard generalized entropy is for the horizon area. And we're discussing spacetimes that differ by quantum excitations from empty de Sitter space or the Schwarzschild black hole. Although we could have done the Kerr black hole similarly. I'm not sure about the Kerr black hole. That might be hard. But anyway, generalized entropy in those cases involves the horizon area. So when I said that we proved that the entropy defined from the algebra agrees with the standard thing, that's in a context where the standard thing involves the horizon area. As I said before in answer to, I think, the first question, I don't know what generalization there is. I stated a highly optimistic generalization, but I don't know if it's correct.
So this renormalization of Newton constants, which you mentioned in the very first part of your talk, it's related to this type 3 algebra goes to type 2 algebra.
Yes, I'd say that the Susskind-Uglum phenomenon that the entropy becomes formal is related to the type 3 becoming type 2.
Thank you very much.
But we missed something. You see, the discussion of the type 2 or type 3 algebra makes sense in the limit that G goes to 0, but the entropy goes to infinity in that limit. So,
sorry, why we need to take G goes to 0 in that argument?
We don't need to take G equals 0, but the discussion makes sense in the limit G goes to 0. In the de Sitter case, I did work in the limit G goes to 0. But you wouldn't expect perturbative corrections to change anything, I said.
I see.
But because the discussion had a limit where G goes to 0, but the entropy doesn't have a limit, it's inevitable that we had to subtract the divergent entropy in the limit. So we don't see the de Sitter entropy, which diverges as G goes to 0. So what we defined was renormalized entropy. So it's entropy up to an additive constant independent of the state. But as up to that constant, it agrees with the standard stuff. It's like classical physics. So classical physicists had relations like this one, which defined the entropy up to an additive constant. But in classical physics, there was no good definition of the constant. And we are in a similar situation. To be able to define the constant, I think you need a type 1 algebra with microstates. I actually have a suspicion, I'm not sure how widely this is shared, but I have a suspicion that there's a clash between having microstates and having classical causality. So, you see, I stated a conjecture before that an observer who sees only part of the universe has a type 2 algebra. But there I was using language, the observer who sees part of the universe, that's sort of classical language involving causality. I suspect that when you use such classical language, you aren't able to see microstates. And a type 2 algebra will be the best possible. If there is indeed always a type 2 algebra for such an observer, which in general is certainly not known.
Thank you very much. Okay, so Tokiro?
Yeah, thank you for the nice talk. And actually, so I want to ask 2 questions. So the first one maybe a long question, but so you said that we can define the renormalized entropy for type 2 algebra, but why we can't generalize such a subtraction to the type 3 algebra? Yeah, I just wonder.
It's because entropies can differ by different infinite amounts for type 3. Well, a type 3 algebra doesn't have a trace, so it doesn't have density matrices. So a type 3 algebra can act on a Hilbert space. It can act on a Hilbert space. And if you have an element of the algebra, you can define the function f of a, which is the expectation value in the state psi. But you can't write this as the trace of a times rho because there's no trace. So to have density matrices and therefore entropies, you need to have a trace.
I see. Sorry, so why if we don't have a trace, then we can't define entropy?
Well, how would you define density matrices? This is the usual definition of a density matrix, and it requires a trace.
Okay, okay, yeah, I see. And the second question is, so you said that we need to introduce observer Hamiltonian for when in compact space case. I think so. And then we don't need to introduce for example in asymptotically flat space. But so if we include even in that case, if we include observer Hamiltonian, even in that case, then so can we get the same algebra without the observer?
Well, we'll get a similar algebra. You see, in the asymptotically flat space, we can define an algebra that acts on all states, whether the observer is present or not. So if the observer is present, we'll just take the operator that acts on all states and restrict it to the code subspace where there is an observer.
So
I'm assuming the observer is more or less at rest at infinity. You see, in an asymptotically flat case, you can gravitationally address operators to infinity, or you can gravitationally address them to the observer world line. But there isn't any important difference between those two.
I see. So if we include the observer where the asymptotic dressed in asymptotic infinity, then so basically we get the same algebra without observer.
Basically, yes.
But if we include an observer in the middle of the space, then that may be different.
If we want to study, for example, an observer who goes behind the black hole horizon, we definitely need to, if we want to do something like that, we definitely need to include the observer in the description.
I see. Okay, yeah, thank you.
Any other questions?
Sorry, I have a question.
Please.
My question is the following. In which part you are using the zeta because it's a closer universe, but in which part you are using this in order to have the
Well,
transition from type 3 to type 2?
Well, I first did the black hole. In the first paper, I did the black hole. Today, I lectured about the sitter space for two reasons. One is I think the results are more interesting and surprising, and secondly, the paper is more recent. So it's more fun to lecture about it.
Ah, okay.
But I'll take your question to be, in today's lecture, where was it important that the universe was closed? So the fact that we had a closed universe made it hard to impose the constraint. The algebra of operators is if A are the static patch operators, then the invariant operators are just C numbers. That's because H generates time translations, and to make an operator invariant under time translations, it has to be gravitationally dressed somewhere. And having a closed universe meant there was no way to do that. We put in an observer and we gravitationally dressed the operator to the observer's world line. In the case of the black hole, we can gravitationally dress the observers to the operators to infinity. So we didn't need the observer. So in the first paper, which was about the black hole, there wasn't any observer assumed. I think it's physically interesting that to get a sensible answer for the sitter space, you need to include the observer. And many people at first reject that, but actually I think it makes sense for reasons I said. I gave one explanation of what it means, namely you're considering a code subspace of states that include an observer, even though the observer in principle is described by the system. But two, in a closed universe with gravity, you shouldn't expect to be able to ignore the fact that the observer is part of the system.
I see. Thank you. Thank you.
As always, I can't make promises. I can only tell you about this analysis of the sitter space. How really one should understand more general closed universes. I can't make any promises.
Any other questions? Any other question? Okay, so I think we have quite many questions, and so
Sir, I had a question.
yes, please, yeah.
Sir, if we include matter in the static patch, like charges and other stuff, how will
Yes.
that influence the
How what?
sir?
I didn't hear the end of the question.
Well, if you include matter and charges, how will that influence algebra somehow?
Well, I explained how it did for weak coupling. We had to replace the constraints by the constraint plus the observer Hamiltonian. So in zeroth or in the limit that Newton's constant goes to zero, all that happens because of including the observer's gravity is that the constraint is modified. In higher orders, of course, more will happen. The observer will be a source of the gravitational field.
And if we include charges and other stuff like that, other kind of interactions other than gravitational, that
We could give the observer a charge in a theory which has gauge fields. If in a theory which has gauge fields, we'd have a constraint that the total charge in the universe is zero. See, that charge isn't, okay. Suppose we add gauge fields. Then in addition to the Hamiltonian constraint, we'd have a charge constraint, and we'd want operators. We'd require that operators are neutral. But there are lots of operators that do commute with the electric charge. There are lots of neutral operators, gauge invariant operators. So having electromagnetism wouldn't force us to worry about the charge of the observer, although we could give the observer a charge. What was different with gravity is that the algebra without the observer was trivial. So we weren't able to impose the constraint on the algebra without including the observer's gravity.
Yes, thank you, sir. That
Okay, so more question? Okay, so if not, then let us thank the Edward for really great talk. Thank you very much.
Oh, well, thank you for the invitation and all the questions. And be well, everybody.
Thank you very much. So actually, this is the end of this our week-long workshop. So I'd like to thank all participants and the great speakers for giving us a nice discussion and the many recent updates of this field. Thank you very much.
Thank you very much.